Swayam Prabha. Digital India. Educated India.
Alright, in this second lecture of module 5 on surface reactions, we continue to look at some typical surface reactions which can involve features very different from bulk phase reactions, allowing for control and monitoring using such ideas as of surface potentials. So, I expect today we should be able to deal with hydrolysis of esters either by alkali, acid or enzymes, and then move on to photochemical reactions in monolayers, and finally consider polymerization in monolayers and another special reaction class called lactonization. This has been kind of general exemplification of applications of interfacial engineering, which in different contexts I have been showing to you. Here if you think of, let us say, one particular area, corrosion or photography, you would be able to see the role of surface reactions. There would be examples in microelectronics also, in build-up of very large scale integration circuits. For example, you make use of photoresist which will combine the action of light with surface reaction, and of course, myriad biochemical reactions that sustain life also occur at surfaces and interfaces. So, I think they have not worked on this. What you do not see here is monolayers of lecithin which can be enzymically hydrolyzed, giving films of lipolecithin. First, let us look at what we were already talking about, the protection of the surface reactive groups by means of a very thin membrane which may be the hydrocarbon layer. The kind of reactions we had begun with, which could be of significance in corrosion and physiology. A few examples you could think of will be like trioleic films and films of erucic and brassidic acid which show similar steric effect, that is protection by a thin hydrocarbon layer of the reactive groups. Or one could even think of oxidation reactions, including those which would involve one of the reactants in the gas phase, such as ozone. Or if you continue on similar lines, the reactions which lead to drying of films containing unsaturation through the well known mechanism of attack of double bonds by oxygen in presence of UV, these could be other surface reactions. We return to the hydrolysis of long chain esters by acid or alkali in the substrate. An example we could take is of ethyl palmitate molecules which may be tightly packed in the surface. If we have such a situation, it is possible to show from measurements of surface potentials that ethyl chains actually are forced down into the water below the reactive carbonyl links, protecting them from the attack by acid or alkali. And this layer of hydrocarbon chains could therefore retard the observed hydrolysis to just about 12% of its rate when this effect does not come into picture. The 4 ethyl groups can have that much effect on the extent of reaction. And experimental studies on such ester hydrolysis confirm the use of equation 4, which is basically the proportion of ln of delta V minus delta V at infinity to time. It is possible to conduct quantitative measurements for such surface reactions, and if we take this example of hydrolysis of stearolactone monolayers on alkaline substrates in this concentration range 0.4 to 2 normal, the reaction velocity constant at 25 degrees centigrade could be measured to be 8.4 plus or minus 1 into 10 raised to minus 2 per minute per mole liters. And then we finally come to enzymic hydrolysis at surfaces containing long chain esters. Once again we see here a similar steric effect, that is, a protective sheath of hydrocarbon chains can prevent the reaction at the ester linkages. There are some interesting examples along this line. We could think of ethyl butyrate hydrolyzed by pancreatin, an enzyme, and this could be done in an emulsion where drops of ethyl butyrate are attempted to be hydrolyzed by pancreatin. This happens readily. However, on very similar lines, if we have an emulsion of ethyl benzoate instead of ethyl butyrate, then we find that there is hardly any reaction. Ethyl benzoate is not digested at all under otherwise same conditions. What would this suggest? This would imply that the bulky benzoate rings would hinder approach of pancreatin to the surface of drops. So, while ethyl butyrate is easily hydrolyzed, ethyl benzoate now suffers from the steric effect. Monolayers of lecithin can also be enzymically hydrolyzed, and this hydrolysis yields films of lipolecithin. This might sound strange, but reactions of lecithin giving lipolecithin are enzymically effectively done using snake venom enzymes. Now, we could see the effect of film pressures. When the film pressures are high, the rate of attack of the film by enzyme in the solution is reduced by a factor of 14. This needs a little bit of reflection. What could possibly be happening? This suggests that enzyme of the venom must require to be coupled not only with the unsaturated hydrocarbon chain which gets hydrolyzed, but also with some other point in the lecithin molecule. If we compress the lecithin film, it would alter the spacing between these two essential points of attachment, and then of course the rate of reaction would be affected by the surface pressure. Protein has a remarkable protective effect on the monolayer of lecithin. An example is oval albumin, when used, could reduce the rate of attack of the venom of black tiger snake by a factor of 10. Lecithinase on monolayer of lecithin can be conveniently studied by radioactive tracer method, and normally this enzyme lecithinase hydrolyzes only lysophospholipids, and it attacks the monolayer of lecithin only if it contains small amounts of diacetyl phosphoric acid or other similar molecules. When we try to analyze and explain this, it becomes clear that an electrical charge on the surface is necessary to attract some part of enzyme molecule close to the monolayer. In addition to this action of the electrical charge, we have the weak van der Waals interaction between the enzyme and the lecithin monolayer. Now, only when these factors act together, can the enzyme be attached sufficiently closely to the surface to cause hydrolysis. Now, experimental complexities in the dependence of the rate of surface pressure, rate in the dependence of rate on the surface pressure and the charge could be due to the additivity of these two energy, electrical and van der Waals attractions. I had mentioned the photochemical reactions and their anisotropy in interception of light as being dependent on the surface pressure. We expect here that the chromophores, which are absorption sites in the molecules undergoing photochemical reaction, would be oriented differently depending on the pressures. So, we expect quantitatively experiments to reveal a variation in the apparent quantum efficiency. Now, the orientation which could be exactly deduced from the measurement of the apparent vertical dipole moment of molecules could be the reason for the different apparent quantum efficiencies measured. This only shows you the effect of the area per molecule on the apparent quantum efficiency, better shown in next figure, where we have the line here showing how the apparent quantum efficiency would vary depending on the area per molecule, which varies from 22 to about 34, and the apparent quantum efficiency span a range of values from 0 to about 0.35. The circles over here are the experimental data points. So, it clearly shows the apparent quantum efficiency of photochemical decomposition of films of stearinolite on 5-normal sulfuric acid. The lines are the theoretical calculations based on the surface dipole moment mu d of the molecules. And as the film is compressed, the orientation of the anilide chromophore group changes and you get the expected increase in the apparent quantum efficiency. We also have photochemical decomposition of stearinolite leading finally to the film of stearic acid. In the process, the aniline, which is one of the products resulting through the surface reaction, sees a high concentration in the surface compared to the bulk and diffuses away into water below this monolayer as fast as it forms. And such results have also been seen with photolysis of benzyl stearyl amine and beta phenyl ethyl stearyl amine, as well as for photolysis of proteins. Next, we talk about polymerization within a monolayer. Once again, we expect the orientation of reactive groups at different film pressures to come into picture. Such is the case with, let us say, the films of malic anhydride compound of beta eleostearin. When polymerized at higher film pressures exhibits a faster reaction under certain conditions. But contrast this to what would happen if we had the same film reacting with an oxidizing agent in the solution below the monolayer. At higher film pressures, this proceeds slower. So, depending on the type of reaction that we have and the extent of the effect of surface pressure on the orientation, we could get quite different results. A number of reactions in monolayers between amines and aldehydes have also been studied, especially in Russian literature. We next come to, yeah.
Suppose surface pressure is increased.
Right.
And seeing it this way, we can say that the concentration on the surface is increased of that particular
Right.
reaction.
Yeah.
So, considering the previous case in which surface pressure led to the slower proceeding of the reaction, so does that mean the concentration is inversely proportional to the rate?
If we actually evaluate the rate data, we might find that indirect dependence reflected in the reaction rate, but here we are only worrying about what effect the orientation, which depends on the surface pressure, could have on the rate of reaction in general. If you find that the rate of oxidation of such polymeric compounds, this malic anhydride compound, if that reduces upon increase in pressure, then clearly the effects are different. What we want to show here is the depending on the orientation and depending on the type of reaction, we might get even opposite effects. Right. Okay, we then return to the, maybe at this point I can also give you an example of how the drying oils solidify. You probably are aware of this situation. Drying oils like linseed oil or castor oil tend to have certain degree of unsaturation. So, you could think of a smooth surface of clean wood, if it is coated with a film or a layer of a drying oil and left to itself to undergo whatever changes under atmospheric conditions, then over a period of time what you find is that the film becomes solid, thin film of this drying oil becomes solid. That is why we call it a drying oil. The unsaturation or double bonds are attacked by oxygen in presence of UV and cross linking occurs. So, that is again a kind of polymerization reaction. Here of course, one is thinking of a spread film with no attempt to change orientation in any way, but if we were to think of doing that, it would become clear that depending on the orientation of these double bonds, the rates of drying could be different. Now, lactonization is a reaction which sort of is intramolecular. There is a reaction between OH and COH groups to produce a ketone. So, we could take an example here. A lactonization which is catalyzed by acid can also occur as a monolayer reaction and it has marked steric effect. We could take an example of gamma hydroxysteric acid. How would the lactonization occur and what are the factors which might influence it, and why we are interested in lactonization over here. First, this reaction offers the possibility that we may be able to represent what is happening at the surface strictly mathematically. So, it becomes that much more amenable to analysis, and besides, lactonization of gamma hydroxysteric acid includes two reactive groups, both held within the film. This will become clear when I show you the diagram a couple of slides later, but let us look at what happens when you change the film pressure. At high film pressures, there is a retardation of this reaction, and this retardation is a direct function of the number of hydroxyl groups forced out of the aqueous interface. We could actually calculate the fraction of hydroxyl groups forced out at any surface pressure, either from the surface pressure directly or from measurement of surface dipole moments. and then this fraction of hydroxyl groups forced out of the aqueous solution could be compared with the experimentally measured decrease in the rate of hydrolysis. You could see this when I show you this sketch of a molecule of gamma hydroxy stearic acid. We are just showing the groups of interest, the hydroxyl group and the COH group at high film pressures, at high values of pi. We are forcing these OH groups away from the aqueous hydrochloric acid over which this film is, and under these conditions of increased film pressures or surface pressures, the lactonization proceeds quite slowly, because now the OH group is not accessible for the action of this acid over here. If this is the condition at high pressures, you could imagine what might possibly happen if we were to take small film pressures. If we look at small values of pi, then it is clear that any such film will have to be resisted from spreading by applying certain restricting back surface pressure. Otherwise, we expect this OH will come in vicinity of the aqueous solution. If this is the condition, OH is forced away from the aqueous solution at high pressures. At lower pressures, this molecule would tend to lie down on the surface, so that OH group now also resides in contact with the acid, right. So, with that imagination, this will be borne out. We have now at lower pressures the OH groups and COH groups both in the vicinity of water plus HCl, and therefore, now you find that the reaction rate would be higher. This lactonization now occurs readily at low film pressures. So, this kind of gives you a little insight as to what special effects the surface reactions could exhibit as opposed to the bulk phase reactions, especially when intramolecular reactions are involved. Now, let us look into the electrical factors a bit ahead of time. At a surface, the kinetic effect of electrical charge is much more pronounced than in bulk. And what are the reasons? First, all the electrical lines of force, instead of radiating in a spherical symmetry as from an isolated charge, we have now all these electrical lines of force concentrated in the region close to the surface, just below the film. I had shown you the line diagram of electrical force fields when we have a charged film at the surface. You see that within a few angstroms, the lines of force become almost parallel to each other. And that being the situation, in the surface, we get a lot higher density and therefore correspondingly very steep electrical gradient. And what may surprise you is that the electrical gradient could be locally as high as 1,000,000 volts per centimeter. So, if I tie up this observation with the comments I made earlier, you would be able to see very high surface concentrations for species which are adsorbed at the surface or spread in the surface. You encounter very high surface viscosities in the surface. You can have equivalents of hundreds of atmospheres of bulk pressure in the surface. Now, we see when electrical factors come into picture, the electrical gradients could be so huge. So, those reactions which may not be possible in bulk phase conditions could be amenable to the action of these electrical factors in the surface. Now, effect of surface charge remains important relative to this kT, the thermal energy, to distances of the order of several hundred angstrom units from the surface, which means in the vicinity of the surface or in the surface space you could have electrical factors dominating over the thermal energy. The second point is the effective concentration at the interface can be very high, and this will be particularly true if the long chain ions are unable to dissolve into the bulk. That may be aided by the fact that a long hydrocarbon chain such as 20 carbon atoms may be hard to dissolve from the surface into the bulk, and therefore, these ions will be packed much more densely than would ever be possible in the bulk solution. An electrical film of charged monolayers can alter the concentration of soluble ions near the interface. A film of long chain anions has but a few OH ions immediately subjacent to it. In the hydrolysis of a monolayer of monocetyl succinate ions, the rate constant K is not constant at various NaOH concentrations in the bulk for obvious reasons. We could analyze this situation looking at the potential psi near the film, and expectedly it would be a function of ionic strength of sodium hydroxide solution. The concentration of the hydroxide ions OH minus or of H plus ions at the monolayer level is neither equal to nor proportional to bulk concentration of alkali. It is rather given by the Boltzmann equations which are we are familiar with, and those are SOH minus equal to BOH minus, that is the surface concentration of hydroxide ions is equal to bulk concentration of hydroxide ions into exponential epsilon psi by kT. Similarly, SH plus is equal to BH plus into e power minus epsilon psi by kT, S and B representing surface and bulk respectively. Epsilon is the electronic charge and psi is the potential. Differences between these two concentrations increases when psi is large, that is at low ionic strengths. Now, you could think of presence of a neutral salt like NaCl added to the solution of alkali on which a monolayer of monocetyl succinate is being hydrolyzed. By adding neutral salt, psi can be reduced very considerably, and that means salt unexpectedly acts as a catalyst, and it may increase the velocity of hydrolysis by a factor of 2 or 3. Quantitatively, this means we must retain SOH minus in our older equations 1 to 4. Remember, at that stage we had replaced SOH minus by BOH minus. We should not be doing that now. Now, the surface and bulk phase concentrations are very different for charged monolayers. So, it is important to understand the circumstances that we are addressing while we attempt to explain the actual accidental scenario with the help of equations. Every assumption has to be carefully weighed before we take the analysis further. Here is a picture of accidental results on rate constant in minute inverse, mole inverse, liter into 10 to the power 3 over this range from 0 to 50, and on x axis we have the added sodium chloride concentration, and that is normality from 0 to 5. As the concentration of NaCl increases, we see the rate of this reaction, alkaline hydrolysis, increases, and the theoretical predictions for a thickness corresponding to about 10 angstroms would help you predict the increase, not of course in complete qualitative agreement. So, we should be satisfied with the simple application of theory here, where the effect of salt as catalyst could be at least semi qualitatively predicted. The monolayer here bears a net negative charge and this repels similar charge OH minus ions. The height of the repulsive barrier, electrical repulsive barrier, is reduced by the neutral salt. So, we need to write instead of equation 1 the following one: dNr by dt is equal to kNr SOH minus, where K is the rate constant, Nr is the surface concentration of reactive molecules, and SOH minus is the surface concentration of hydroxide ions, which we substitute by BOH minus exponential epsilon psi by kT. For given values of the rate constant K and the bulk concentration of hydroxide ions, this implies that one may generally write rate of reaction in the charge film by the rate of reaction in neutral film as equal to exponential minus Z2 epsilon psi by kT. In case of uncharged film, psi would be 0, where Z2 is the valency of the counter ion, which is -1 for OH minus ions, and this equation can be applied to hydrolysis also by acids. H plus in that case will be corresponding to Z2 of +1. For alkaline hydrolysis of monocetyl succinate, this means that we will have the reaction slower than if the film were neutral, or if NaCl were added to reduce the value of the potential psi to a very low value. If however psi is positive, Z2 is -1, the reaction will proceed more rapidly on account of the charge, and this is found in alkaline hydrolysis of octadecyl acetate monolayers, into which a little amount of these long chain cations, C18 cations, have been incorporated. So, this basically tells you that it is possible now to use the greater number of degrees of freedom that are offered by surface reactions to achieve practically attractive reaction rates by making gentler choices, small surface pressures, incorporation of surface active ingredients, changes in pH, and intelligent use of the interaction of van der Waals forces with the electrical forces in many different ways. So, with this I think we get some idea about the flavor of surface reactions in a wide cross section. So, for today we will stop here.